Hello and welcome to Lecture 1 of our course on stochastic modeling of biological processes, which is recorded here at the Mathematical Institute, University of Oxford. We will discuss Chapter 1 in our first three videos, named Lectures 1, 2, and 3. In this first video, we will focus on first two sections covering pages 1 to 14 of our lecture notes, which is this textbook called Stochastic Modeling of Reaction Diffusion Processes. The following video will discuss how to implement stochastic simulations on a computer, and we will conclude in lecture 3 with the remaining three sections of chapter 1. I have included some examples of chemical reactions here. The first one describes the chemical species called A, which is removed from the system with the rate constant K1. Here two chemical species A and B react with the rate constant K2 to produce the product called C. Here two molecules of A create a dimer D, and this reaction can go in both ways. In all these examples and in our lecture notes, we denote chemical species by capital letters like A, B, C, and D here. In applications, they will have specific biological names. I have put the phrase chemical reactions in quotes here because this chemical reaction formalism can be applied beyond traditional chemistry. In applications to modeling gene regulatory networks, chemical species will denote different types of proteins, while in modeling of ecosystems, chemical species could become populations of predators and prey, and these arrows will denote the corresponding interactions. We will see some examples later, but first of all we have to build some solid mathematical foundations. Following the analogies which we discussed in our lecture 0, we can divide mathematical models for systems of chemical reactions into deterministic and stochastic modeling. Here deterministic models are written as systems of ordinary differential equations, abbreviated as ODEs. Some of you might have taken courses on such modeling, but we will not assume this. It is actually quite straightforward to translate the chemical reaction formalism into the corresponding ODEs. It is summarized in the appendix of our lecture notes, and we will also explain it on examples in chapters 1 and 2. The corresponding ODE will be formulated for each example, so you will quickly learn how to construct deterministic ODE models, even if you have not yet had any courses on this type of modeling. Our main focus will be on stochastic modeling. We will introduce stochastic simulation algorithms, abbreviated as SSAs. We start with a simple example, a single chemical reaction on page 1. This chemical reaction describes a single chemical species called A, which is removed from the system with rate K. In what follows, this mathematical symbol, empty set, will denote all chemical species which we do not explicitly model. That is, this chemical reaction could model different chemical processes, including a conversion of chemical species A into another chemical species, say B, or even a reaction with multiple products. However, since we are only interested in the behavior of A, we will not explicitly describe the products of this reaction, and we replace all unimportant chemical species by this symbol. Let us first start with the deterministic modeling of this reaction 1,1. In this case, the state of the system will be described by the concentration of chemical species A at time t, which we will denote by lowercase a t. This concentration satisfies the following ordinary differential equation. The rate of change of A, dA over dt, is equal to minus Ka. We can either treat this ODE as the definition of the deterministic model of this chemical reaction, or we can define that the product of K, At, and dt gives us the change of the concentration over a small time step of length dt. Rearranging and passing to the limit dt goes to 0, we obtain this ODE, which we can solve analytically to obtain that its solution is just this exponentially decaying function, where A0 is the initial concentration. For more complicated examples, we will not have an analytical solution, but we can still solve the corresponding deterministic ODE model numerically. The concentration of chemical A is plotted here as a function of time for the initial condition A0 is 20. In this case, we know that the solution, this curve, is just an exponentially decaying function of time. Next, we will discuss stochastic modeling of degradation. In this case, we describe the state of the system in terms of the number of molecules of chemical species A at time t, denoted by AT. So AT is a non-negative integer. Then this symbol, chemical reaction 1,1, can be defined in terms of this probabilistic definition highlighted here in red. The probability that a molecule is degraded in a very small time interval dt plus dt is AT times K times dt. This definition can immediately be used to design a computer algorithm for simulating the time evolution of the system. It is given on page 2 of the lecture notes, where we call it a naive SSA, where the abbreviation SSA stands for Stochastic Simulation Algorithm. SSA is a method for the computation of the state of the system at a future time from the current state AT. To design this naive SSA, we simply replace the infinitesimally small time step dt by a small time step delta t. At each time step, we repeat these two steps. First, we generate a random number r uniformly distributed in the interval 0, 1. If r is smaller than ATK delta t, then the reaction 1, 1 occurred, and we update the state of the system by removing one molecule of A. Otherwise, we will do nothing. By repeating steps A1, B1, we can compute the time evolution of the system, which is shown in figure 11a on page 3 of the lecture notes, where I start with 20 molecules in the system. Molecules are removed from the system one by one, so after 20 occurrences of our degradation reaction, there is no molecule left. As you can see with this blue realization of our algorithm. Repeating the same simulation, again, we obtain a similar result, this red realization. But it is not exactly the same. It depends on the random numbers which we sampled during the simulation. In this red realization, it took a longer time to get to the final state with no molecules in the system. For comparison, I also added here the ODE solutions which we obtained previously. For this simple model, the ODE solution describes the average behavior of our stochastic model. We will prove this in a short while, but before doing that, let us first discuss the accuracy and efficiency of our naive stochastic simulation algorithm A1B1. We defined reaction 1,1 by stating that the probability that exactly one reaction occurs during the infinitesimal time interval tt plus dt is equal to AT times k times dt. To design the SSA A1B1, we replace dt by the finite time step delta t. In particular, we must ensure that AT times k times delta t is significantly less than 1 to get reasonably accurate results, because we have to make sure that the probability that two reactions happen during one time step is negligible. To obtain the previous illustrative results, I used k equal to 0,1 per second, and I chose the time step delta t so small that ATK delta t is less than or equal to 0.01 for any time t. Since the probability of a reaction occurring during one time step is less or equal to 1% or 10 to minus 2, the probability of two reactions taking place is about 10 to minus 4. Therefore, the simulation error is negligible, and it could even be made smaller by choosing an even smaller time step. However, choosing the time step delta t smalls makes the naive SSA extremely inefficient. In our case, the probability that the reaction 1,1 occurs during the time interval tt plus delta t is less than or equal to 1%. Put differently, there is probability 99% that no reaction happens during one time step. Therefore, during most time steps, we generate a random number r in step A1 only to find out that no reaction occurs in step B1. We can do much better than that. The key to improving the algorithm A1B1 is a change in viewpoint. Instead of focusing on time, we focus on events. Rather than stepping forward in time and asking, did a reaction take place? We ask at what time will the next reaction occur. In this way, we will design an algorithm which will not only be more efficient than the naive SSA A1B1, but it will also not include any approximations. To do that, let us return back to our definition of the chemical reaction 1,1. We postulate that the probability that a molecule is degraded in time interval tt plus dt is equal to ATK dt. Consequently, the time interval to the next reaction, tau, is distributed according to the exponential distribution with mean 1 over ATK and can be sampled by using this formula. Tau is equal 1 over the mean of the exponential distribution times logarithm 1 over r, where r is a random number uniformly distributed in the interval 0, 1. In Oxford, students taking this course also took a basic course on probability in their first year, where Formula 1.5 for sampling exponentially distributed random numbers is derived. So I will not reproduce its derivation in this video. However, if you are unfamiliar with this result, you can find the detailed derivation of Formula 1.5 on pages 3 to 5 of the lecture notes. This formula gives us an alternative way to simulate the time evolution of the system, which is introduced as algorithm A2C2 on page 5. At time t, we perform the following three steps. First, we generate a random number r uniformly distributed in the interval 0, 1. Then, we transform it to the time when the next reaction occurs using the derived formula. Finally, we remove one molecule of A from the system by calculating A at time t plus tau as A at time t minus 1. Two illustrative realizations of algorithm A2C2 are plotted here. I again use the same initial condition as before. We have 20 molecules at time 0. After 20 degradation events, we end up with no molecules of A in the system. In particular, we only need 20 iterations of our improved algorithm before all molecules are degraded. This is a significant improvement in efficiency when compared with the naive SSA. Remember that we need to generate on average 100 of random numbers to calculate the time of the first degradation reaction. Now we only need one random number to find the time when the first molecule is degraded. Therefore, our improved algorithm is about 100 times more efficient. Not only that, SSA A2C2 is also more accurate than the naive SSA because it exactly simulates the underlying stochastic process. In my next figure, I replot the ODE solution, this exponentially decreasing function, which we discussed previously. I also include 10 realizations of the SSA A2C2, which are plotted in figure 11b. Since it is so efficient to calculate individual realizations of our improved SSA, we can easily calculate millions of stochastic realizations and we can average over these results to obtain the expected number of molecules in the system at time t. Looking at the 10 realizations plotted in this figure, we could hypothesize that our ODE solution could provide a good description of the average behavior of the system. And we can prove this. To prove this, we first need to rewrite our stochastic simulation algorithm, our computer code, in terms of mathematical equations which we can analyze. We will describe the state of the system in terms of the probability that A at time t is equal to n. That is, the probability that there are n molecules of A at time t, which we denote as P and T. Here n is a non-negative integer. The stochastic model of reaction 1,1 was given using this red definition. The probability that a molecule is degraded in time interval tt plus dt is equal to ATK dt. Next, we will use this red definition to write an evolution equation for probability P and T. Let us consider a small time step dt and let us calculate the probability that there are n molecules of A at time t plus dt. There are two possible ways for A to take the value n at time t plus dt. Either A was equal to n with probability P and T and no reaction occurred in the time interval t plus dt with probability 1 minus k n dt. Or there were n plus 1 molecules of A at time t and one molecule was degraded in the time interval t plus dt, which happened with probability k times n plus 1 times dt. Taking the term p and t on the left hand side and dividing the whole equation by dt, we obtain the following equation. On the left hand side, we see a discretized derivative of p and t. So we pass to the limit dt goes to 0 to obtain the so-called chemical master equation in the following form. The time derivative of Pn is equal to Kn plus 1 Pn plus 1 minus Kn Pn. The chemical master equation is equivalent to the SSA and will be our starting point for the analysis of simple chemical systems. So you should be able to derive it for any chemical system. We will see a few more examples of chemical master equations in our initial lectures. It is an equation for probability which contains two terms on the right hand side for each reaction, the gain term and the loss term. To derive the chemical master equation, we use this equation, where we consider that the time step dt is chosen so small that the probability that two molecules are degraded during the time interval tt plus dt is negligible compared to the probability that only one molecule is degraded during this time interval. In fact, the probability that two reactions happen during one time step is proportional to dt square. If we included such terms in this equation, then they would all converge to 0 in the limit dt goes to 0. That is, they will not influence the derived chemical master equation, which we obtained in the limit dt goes to 0. In particular, the chemical master equation describes the SSA exactly, without making any approximations. The chemical master equation looks like an infinite system of ordinary differential equations, ODEs, for Pn, where n is a non-negative integer. However, our initial condition A0 is equal to n0 implies that there are never more than n0 molecules in the system, so that Pn is identically equal to 0 for n greater than n0. Therefore, the chemical master equation 1.6 is in fact a finite system of n0 plus 1 linear ODEs for P0, P1 until Pn0. Since it is a linear ODE system, it can be easily solved to obtain the following formula, which is the probability mass function of a binomial distribution. Properties of the basic discrete probability distributions are summarized in Appendix B on page 295. Since AT has a binomial distribution with parameters n0 and exponential minus kt, the mean of the binomial distribution is just the product of its parameters. So the average number of molecules at time t, the expectation of AT, is equal to n0 times exponential minus kt. If you don't know this result, then it is derived in detail in the lecture notes as equation 1.8 on page 7. This formula is exactly what we obtained when we solved the deterministic model. In fact, in exercise 1.1, you can show that the evolution equation for mean MT is equal to the deterministic ODE. Such a result is true for any so-called first-order reaction network, but it is not true in general, as we will see in a number of examples starting from lecture 3. Therefore, the time evolution of the mean number of molecules in figure 1.1b can be computed by an analytical formula. The same dashed line can also be computed by averaging over millions of realizations of the SSA. And it is exactly the same exponentially decreasing curve as the ODE solutions we studied previously. The degradation reaction eventually leads to the elimination of all molecules of chemical species A. We now make the dynamics of the system more interesting by adding also some production of molecules of A. Therefore, our next example, studied in section 1.2, is a system of two chemical reactions. The first one is the degradation reaction with the rate constant K1. The stochastic model of this reaction was already discussed before. It is given as this red definition. The probability that a molecule is degraded in the small time interval Tt plus dt is equal to At times K1 times dt, which we have rewritten as alpha 1 times dt, where alpha 1 is the propensity function of the first reaction, defined as At multiplied by the rate constant K1. In general, the propensity function of a reaction is what stands in front of dt in this probabilistic definition. The second reaction is the production reaction. To formulate its probabilistic definition, we define its propensity function alpha 2 to be a constant. It is a product of the reaction rate constant K2 and the volume of the system, which we denote in this chapter by this symbol nu. With this notation, the probabilistic definition of the second reaction is given as this red definition. That is, the probability that one molecule of A is created during the time interval Tt plus dt is equal to alpha 2 times dt. Obviously, all probabilities are dimensionless numbers, so we have to note here that the rate constant K1 and K2 have different physical units. The rate constant K1 is expressed in the units of 1 over second, while the units of the rate constant K2 are 1 over volume and over second. It is the production rate per unit of volume and per unit of time, so that the probability that one molecule of A is created in the whole reactor is K2 nu dt, where nu is the system volume. With these definitions, we can immediately write the stochastic simulation algorithm for our chemical system. It is given as the SSA A3D3 on page 9. In the first step, we generate two random numbers R1 and R2 uniformly distributed in the interval 0, 1. Next, we calculate the total propensity function alpha 0, summing the propensities of individual reactions. Then we know that the time to the next occurrence of a reaction is exponentially distributed with mean alpha 0, so that we can sample it using the formula 1 over alpha 0 times logarithm 1 over R1. Therefore, step C3 calculates the time when the next reaction occurs. Finally, we have to decide which of the two reactions took place at time t plus tau. We know that the probability of the second reaction occurring is its propensity alpha 2 divided by the total propensity alpha 0, which is K2 nu divided by alpha 0. Therefore, we use the second random number R2 to decide which reaction took place. If R2 is less than the probability of the production, then the production reaction occurs at time t plus tau, and we add one molecule of A to the system. Otherwise, it was the degradation reaction which occurs at time t plus tau, and we remove one molecule from the system. By repeating the 4 steps of the SSA A3D3, we simulate every reaction event. This SSA is the special case of the Gillespie algorithm, which we will discuss in the full generality in lecture 3. Illustrative results computed by the SSA A3D3 are presented in figure 1.2 on page 10. Since computer simulations form an important part of this course, I will discuss in detail in the next lecture how the SSA A3D3 can be implemented in MATLAB. Figure 1.2 has 2 panels. On the left panel, you can see 5 realizations of the SSA A3D3, each starting with no molecules of A in the system at time 0. Initially, some molecules are produced, then some are degraded, but after about 50 seconds, the number of molecules fluctuates around the value of 10 molecules. The dashed line is the average number of molecules in the system. It can be obtained by averaging over millions of stochastic realizations of the SSA A3D3, but we can also obtain the mean analytically. We will next discuss the corresponding analysis. Our chemical system has been so far described using the SSA A3D3, which is effectively a computer code. To obtain some theoretical results, we have to equivalently describe the behavior of our computer code in terms of suitable mathematical equations for probability P and T, which is again the probability that there are n molecules of A at time t in the system. Therefore, the starting point of our analysis will again be the corresponding chemical master equation, which is given as equation 111 on page 10. In this case, n can be an arbitrary integer, because in theory, this production reaction can happen arbitrarily many times between two degradation reactions. In particular, P and T is non-zero for any non-negative integer n, and the chemical master equation is a system of infinitely many linear ODEs. Each chemical reaction corresponds to 2 terms on the right-hand side of the chemical master equation. This is the gain term and the loss term corresponding to the degradation reaction, and this is the gain term and the loss term corresponding to the production reaction. We are interested in the behavior of the mean and variance of the random variable A, which are defined as these sums. In section 1.1, we first solved the chemical master equation 1.6, and then we used its solution 1.7 to compute mean MT. An alternative approach is to try to use the chemical master equation to derive evolution equation for mean and variance. If we can do this, we can find mean MT without having to first solve the chemical master equation. To find the evolution equation for mean, we can multiply the chemical master equation by n and sum over all n. Then the left-hand side is the time derivative of the mean, and the terms on the right-hand side simplify to minus k1m plus k2 nu. Thus, we have obtained an ODE for the mean. In general, this technique will work for the so-called first-order reaction networks, that is, for reactions which only include one or zero reactants, as it is the case for our production degradation example. However, starting in lecture 3, we will see other chemical systems when the evolution equation for the mean cannot be derived using this technique. While it is always possible to multiply the chemical master equation by n and sum over n to obtain the time derivative of the mean on the left-hand side, we cannot simplify the right-hand side for general chemical systems. However, in the case of our simple production degradation example, this technique can be further generalized to derive evolution equations for arbitrary moments. For example, to obtain an OD for the second moment, we multiply the chemical master equation by n squared and sum over n. In particular, we can also derive the following ODE for the variance. Therefore, in figure 1.2, this black dashed line can be obtained by solving this ordinary differential equation for mean m with the initial condition that mean at time 0 is 0, which gives this formula. We can also calculate the stationary value of the mean ms either from this ODE by putting the right-hand side equal to 0 or from this solution formula. We obtain that ms is the ratio of the reaction rates K2 nu divided by K1, which for our parameter values is equal to 10. The stationary variance is also equal to 10. In addition to the stationary mean and variance, we can also calculate the whole stationary distribution, which is given in figure 1.2 in the panel on the right. To obtain the stationary distribution from the stochastic simulation algorithm, we can follow one stochastic realization for a very long time and record the values of A at equally spaced time intervals. We observe that the probability that there are 10 molecules in the system is about 12%, and the probability that there are either 5 or 15 molecules is smaller, about 4%. Again, we can theoretically calculate the stationary distribution. To do this, we start with the chemical master equation 111 and we observe that the plotted stationary distribution can be obtained as the limit of P and T as time t goes to infinity. We denote it as phi. It is a time-independent probability mass function which satisfies the stationary chemical master equation, which has 0 on the left-hand side. It relates the values of phi at n plus 1, n, and n minus 1. Therefore, one possible way to solve the stationary chemical master equation is to rewrite it as an iterative formula, which effectively expresses every value of phi n in terms of the value of phi at 0, which is a constant that can be calculated by the normalization condition. Alternatively, the stationary chemical master equation can be analytically solved using the probability generating function. We will discuss the use of the probability generating function in lecture 3. When we will derive that the stationary distribution is just the Poisson distribution with mean K2 nu divided by K1. Therefore, we again confirm that the variance is equal to the mean, which is equal to 10 for our parameter values. The Poisson distribution is plotted here as the red line. As expected, it compares well with the results obtained by the stochastic simulation algorithm. To summarize our first lecture, we have covered the first two sections of the lecture notes by discussing stochastic simulation of a single reaction, degradation, in section 1.1, and stochastic modeling of a simple system of two reactions, production and degradation, in section 1.2. Please read pages 1 to 14 of the lecture notes before watching lecture 3. Our next lecture, lecture 2, is a MATLAB demonstration. I will discuss how you can design and write a MATLAB code giving you the results presented in figure 1.2. Then, in lecture 3, we will continue with the second half of the first chapter, covering sections 13, 14, and 15 on pages 15 to 29. Thank you for listening to our video lecture of Oxford course on stochastic modeling of biological processes. Bye bye.